In this module, we will look at basic principles of electromechanical energy conversion, and we will look at its role, the structure, how we produce magnetic field, and what are the basic principles for producing force, torque, and how EMF is induced. We will look at how these can go seamlessly from the motoring mode to the generating mode, and we also look at power losses and efficiency. So let's look at this block diagram here, where we see that we have this electrical system and this mechanical system, and electric machine or drive, if you will, is in the middle, and in the motoring mode, power is going from the electrical system to the mechanical system here. But when this machine or drive goes into generating mode, then the power is coming from the mechanical system and is going into the electrical system. So there may be machines which operate mostly on the motoring mode, but sometimes they go into so-called regenerative braking mode, so they become a generator, but some of them are designed primarily to be, are always to be a generator, for example, in a wind turbine. So let's look at the basic structure. These machines are usually cylindrical as shown here, and if we cut them by a plane perpendicular to the axis of the shaft and look from one side, what we see here is that we have a rotor here, and then there's a stator. So rotor is here and the stator is here, and there's an air gap in between that has to be there so the rotor can turn, and the stator is affixed to this foundation over here. So there are two-pole structures as shown here, or you could have 4 poles as shown here. So you have a north and north here, so the flux is going in and is coming out at the south pole over here, or you could have pole structure over here. The south probably should be here and here, and you can see that the flux is going out from the north pole as coming into the south poles over here. So this is a round rotor structure. Similarly, here is a round rotor structure, where here is we have a salient pole structure. So before anything can happen in these machines, we need to produce magnetic field. And we'll assume that this magnetic field is radial in direction, and it can be represented by magnetic field intensity, or MMF, or flux density here. So if you assume that mu is infinite for this iron in the stator and the rotor, then we really need to concentrate on what's going on in the air gap. And so this magnetic field, which we assume to be radial, is positive if away from the center. So when it's going in towards the center, we'll consider that to be negative here. So if you apply Ampere's law here, you can see that we only need to look at the air gap length, L sub g over here. So if you have n sub s number of turns, and I sub s is the current going into it, and you apply Ampere's law, this flux has to go through the air gap twice, so this factor 2 comes in over here. Otherwise, it's the Ampere turns divided by 2 times the air gap length here. But if you just look at the MMF acting on an air gap, then it's really this magnetic field intensity times L sub g, which you can see here would be given by this expression here. And the flux density in the air gap then is just mu naught times this H sub s over here. So we can plot the flux density or the MMF or the magnetic field intensity to different scales as shown over here, and we can see that we will get this kind of a structure here, where rotor surface at the bottom here, the stator surface is at the top, and this angle theta is being measured from here, as you can see here. And so in this very primitive structure, we will have this square wave type distribution. So what are the two basic principles on which most of these machines operate? One is that there is a force on a current carrying conductor, which is in some externally established magnetic field. So let's say that all these quantities are perpendicular to each other, and so the conductor is carrying this current. Conductor is the length L, is carrying this current I, as is in this magnetic field B. So there'll be a force on this, and we will elaborate this a little bit in the next slide. And similarly, if this conductor is moving in a magnetic field, then there's a voltage induced here. So we'll see both of these here. So let's start with electromagnetic force, and best way to look at it is that if there's a conductor perpendicular to plane of this screen, and the current is coming out of this conductor, that is this tip of this arrow is pointing towards us, then the flux lines are, as you can see, counterclockwise due to this current. And then if this is in an external field as shown here, you can see that the flux lines add up on this side and they subtract on this side over here. So that is what is shown here, and the force is in the direction from higher concentration of flux lines to the lower concentration. So it will be from right to left in this direction shown here. And this flux, all these things being perpendicular to each other, it's the magnetic field intensity, length of the conductor, and that the current into it. So that's a very simple expression that we have. And similarly, we can find what the induced MMF would be if, for example, we have flux lines going into the screen of this, into the screen shown by the tail of these arrows, and this conductor of length L is, let's say, moving at this velocity u as shown here. So in this case, the force on these a positive charge is given by this expression, the charge times u cross b, using u and b as a vector, and they're perpendicular to each other in this example. And then you can see that the magnitude of this induced EMF would be b times the length of the conductor times u. And these are all in MKS units. And the polarity of induced EMF is given by FQ. And this polarity of induced EMF would be independent of whether any current is flowing through this conductor or not. All right. So now let's take these two principles into some very basic structure here, very primitive machine, if you will. And so what we have here is some externally established stereomagnetic field, and its axis is given here. And we consider this to be, let's say, radially distributed. And then we have a coil on the rotor, and this coil is being supplied by this electrical system by a current I sub r. And the magnitude of this, the wave shape of this current depends upon the position as shown here. So delta here is being measured with respect to this this reference axis over here in this direction here. So the current is dependent upon this position, and it's plotted like this here. So you can see that between 0 and 180 degrees of delta, this current is positive here of magnitude I. Okay, and we can calculate what the force would be on this coil of n sub r number of turns and length L, and so therefore we can calculate what the electromagnetic torque would be on this coil, which is given by this here. So what happens here is that when delta becomes greater than 180, then certainly magically in this case, this is a very primitive, somewhat hypothetical machine, if you will, this current changes its direction, and from plus I it becomes minus I. So in this case, you can see that the torque that is produced remains constant and a positive value, and the induced EMF in this coil then goes through this square shape waveform here. So the important thing to note here is that this rotor coil is being rotated counterclockwise at this speed omega m, and the torque that is produced in this system is also counterclockwise. So it's in the same direction as the speed. So this is really a motoring mode. That's how a motor works, because if electromagnetic torque is produced, then it will make it rotate in the direction in which this electromagnetic torque is produced. So the other important thing to note is that we have this induced EMF in this coil, and that is given by this expression, making use of that earlier principle that we saw. And you'll see that there's a great deal of similarity between this induced EMF expression and the torque expression here. And that will become clear as we proceed with this topic. The main thing, however, here is to notice that this motoring mode that we discussed earlier could be made into a regenerative braking mode, where now the power is flowing from the mechanical system to the electrical system. So what is happening here is that this rotor is still turning in the counterclockwise direction under the influence of some other means. Maybe it's inertia, maybe there's a prime mover there, but nevertheless it's turning in a counterclockwise direction as in the motoring mode. But here you'll see that the torque is opposing this direction of rotation, and that is because this current I sub r here has an opposite wave shape, if you will. So between 0 and 180 delta, it's a negative value, and outside of that, it's a positive value here as shown here. So as a consequence, the torque that is produced has a negative value. That means it is in a clockwise direction and is opposing the direction of rotation. However, the induced EMF is the same here, has the same wave shape as in the motoring mode here. So clearly, in this case, the power is going from the mechanical system to the electrical system, whereas in the motoring mode, power is flowing from the electrical system to the mechanical system. The last thing we'll look at here is power losses and energy efficiency. So when we have a drive, it consists of this electrical machine, and it has these motor losses. Then it has this power processing unit, the power electronics, and that has its own losses over here. So, the motor losses here consist of the conduction losses within the machine. Then you have hysteresis and eddy current losses, friction and windage, and then the switching losses inside the machine as well, and then some stray losses that we cannot easily account for. So if we add them all, then we have the loss in the mechanical system. And so the efficiency of the machine, we can say, is output power divided by the input power, and this input power is the output power plus this P loss over here, right here. So that is the efficiency of the motor by itself, but in addition, in this power processing unit consisting of transistors and diodes, we have conduction losses and switching losses in these switches. So, this power processing unit has its own efficiency, and to find the overall drive efficiency, we should multiply this power processing unit efficiency with the motor efficiency. And typically, it's in 80 to 90% range. In very large power ratings, it may be approaching 95% or even higher. And then also we have a safe operating area. Quite often it is possible to operate above the rated speed, but one has to be careful and possibly consult the manufacturer whether it's safe to operate there. And certainly one can operate up to, in steady state, the rated torque over here. So here is a safe operating area, and this area is somewhat reduced at lower speeds because there we have less cooling going on. And so that torque that we can have is reduced at lower speeds. And it's possible to operate this continuous safe operating area under transient and intermittent operation. So this brings us to the end of this module where we have looked at the basic principles of electromechanical energy conversion, its role, structure, how we produce magnetic field, how force and torque, as well as EMF, they are EMF induced, and we looked at motoring and generating modes, how it can go seamlessly from one mode to the other, and power losses and efficiency in these systems.